What do you mean by nanotechnology? It is the study and application of extremely small things and can be used across all other science fields such as chemistry, biology, physics, material science, and engineering, which about 1 to 100 nanometers. To give additional information of what nanometer is, let's watch this.
Let's make the almost inconceivable nano world conceivable. The naked eye can see the diameter of a human hair. That's 1/10 of a millimeter, or 100,000 nanometers. To understand the small, we're going to scale it up to skyscraper proportions. And return to our human hair and blow it up to the size of the Empire State Building. A typical human cell, say a red blood cell, would rise to the 10th floor. A bacteria cell, the 3rd floor. Working down our scale, a run-of-the-mill protein molecule would be the same height as a small dog, about 1.5 feet. And a nanometer, on our Empire State scale, it's less than 1/4 of an inch. That's about the size of 5 microscopic atoms placed end to end.
Is the understanding and control of matters at the nanometer scale, where unique phenomena involve novel application. And also, it involves the design, characterization, production, and application of nanoscale structures, devices, and systems that produce structures, devices, and systems with at least one novel, superior characteristic or property. It is hard to imagine just how small nanotechnology is. 1 nanometer is a billion of meter, or 10 to 9 to the power of a meter. Did you know the size of nanotechnology? If you don't know, let's watch this. As a matter of fact, everything on Earth is made up of atoms. The food we eat, the clothes we wear, the buildings and the houses we live in, and our own bodies, but something as small as an atom. It is impossible to see with our naked eye. Although modern nanoscience and nanotechnology are quite new, nanoscale materials were used for centuries. The artists back then just didn't know the process they used to create these beautiful works of arts actually lead to change in the composition of the materials they were working. Today, scientists and engineers are finding a wide variety of ways to deliberate and make materials at nanoscale to make advantage of their enhanced properties, such as higher strength, lighter weight, increased control of light spectrum, and great chemical reactivity than their larger scale counterparts.
For wider understanding, let us all find out how nanotechnology started. The ideas and concept behind nanoscience and nanotechnology started with a talk entitled There's Plenty of Room at the Bottom by physicist Richard Feynman at an American Physical Society meeting at the California Institute of Technology or Caltech on December 29, 1959, long before the term nanotechnology was used. In his talk, Feynman described a process in which scientists will be able to manipulate and control individual atoms and molecules. Over a decade later, in his exploration of ultra-precision machining, Professor Norio Taniguchi coined the term nanotechnology. It wasn't until 1981, with the development of the scanning tunneling microscope that could see individual atoms, that modern nanotechnology began. But how does nanotechnology works? At the core of the nanotechnology is the fact that the properties of materials can be different at the nanoscale for two main reasons. First, nanomaterials is a relatively larger surface area when compared to the same mass of materials produced in a larger form. This can make materials more chemically reactive and affects their strength and electrical properties. Second, so-called quantum effects can begin to dominate the behavior of the matter at the nanoscale, particularly at the lower end, affecting the optical, electrical, and magnetic behavior of materials.
A couple of videos now, we've talked about some of the quantum effects that happen at very small scales, but we didn't dive fully into the details of each. In this video, I'll introduce this new quantum effects series, and some of the effects we'll be covering very soon. Don't forget to hit the like and subscribe buttons, and let's get started. In science, we pretty much separate the world into two areas. One is classical physics, which is all orderly and expected at the large scales, and the other is quantum mechanics, which is all random, unexpected, and based on probabilities at the molecular scale and below. In the quantum world, there are a lot of phenomena that take place routinely that are very different than what we experience every day as we interact with the world in classical physics. There are a few effects that I want to present in this introduction that we'll be covering in this series. Let's start by imagining that we're holding a ball in one hand and that we live in a quantum world. Now, let's imagine that we throw the ball one time, and instead of going towards the wall, hitting it, and bouncing back to us as it does in classical physics, it simply disappears from our hand, appears at the wall, and appears back in our hand without having traveled between our hand and the wall. Well, in the quantum world, this happens all the time, and it's called quantum jumps. Every electron that surrounds an atom will be jumping like this at the different orbitals of the atom as the atom absorbs and re-emits energy. Now let's throw the ball again, but this time it doesn't hit the wall where we were aiming. Instead, it hits the wall way off to the side, which is nowhere near where we were aiming. Well, this also happens in the quantum world because as the ball leaves your hand, it starts behaving like a wave of probable locations of where it will end up. So the further the wall is, the wider of an area the particle can actually end up. Just like a single small rock dropped in water will eventually make waves as large as your house. In this example, the probabilities made it so that the ball hits the wall well beside the area that we were aiming. This is the wave-particle duality of particles in the quantum world, where everything travels like a wave and only collapses with an interaction with the outside world. This phenomenon is called quantum superposition, where a particle is everywhere it can be simultaneously. Another example of superposition is Schrödinger's cat. This thought experiment consists of a box that has a vial of poison inside that's set to disperse at any random moment, and a cat is put inside. Once the box is closed, the cat can be thought of as both alive and dead simultaneously. It's only at the very moment that you open the box that you'll find out whether the cat is alive or dead. Now back to our example with the ball. Let's say we make another throw, but now instead of bouncing back to us, it simply goes through the wall. Well, again, this is something that happens frequently in the quantum world. It's called quantum tunneling. The chances of a particle getting through depends partly on the thickness of the barrier. This is one of the reasons why we can't really continue to make transistors smaller in computers, because the electrons will simply tunnel through them if we do. Next, let's imagine that we both have a ball, and that if I spin mine clockwise on my finger, yours starts turning exactly the opposite of mine counterclockwise. And it does this instantly, even if we're separated by huge distances. So essentially, your ball knows to turn counterclockwise faster than light could have traveled to it to transfer that information. Well, this is another quantum effect that happens very often, and it's called quantum entanglement. Furthermore, quantum entanglement can be used to essentially teleport particles to a remote location without having to physically send it, which we call quantum teleportation. So this was just a quick and simplified overview of some of the quantum effects that we'll be covering in this series. There's a lot more to each than we just talked about here. That's why we'll have videos dedicated to each effect so we can cover them properly. There's also more quantum effects than the ones we just talked about, so if there's a lot of interest in this series, we can always dig deeper in other quantum effects and how they work as well.
Nanotechnology and the future of advanced materials. Nanotechnology future products are based on the present and future development of a large spectrum of nanomaterials. The development of a huge variety of nanomaterials will lead to a radically new approach to manufacturing materials and devices. Basically, every aspect of our life will be impacted. These are some areas where nanomaterials will have a major impact. Faster computer, biocompatible materials, controlled drug delivery, nerve, and so on. Nanotechnology has a basic building blocks. They are nanoparticles, nanomedicine, and nanobiotechnology. Let's define what is nanoparticles. Nanoparticles are used in a broad spectrum of applications and many products. They are distinct in their properties and applications. In addition to that, nanoparticles vary in chemical composition, shape, surface characteristics, and mode of application. Let us define what is nanomedicine. Take for example nanotechnology in medicine. The medical advances that may be possible through nanotechnology range from diagnostic to therapeutic. Nanomedicine is expected to make diagnosis possible at the cellular and even subcellular level. Last is the nanobiotechnology, also known as bio-nanotechnology, biomedical nanotechnology, or nanomedicine. It uses biological steering materials, biological design principles, or has biological or medical application.